Welcome to Mr. Hamilton's Math Bites. This video is about linear quadratic systems. If you thought grade 9 and points of intersection of two straight lines was fun, wait till you start linear and quadratic intersections. Then again, for some of you, perhaps fun is too strong of a word for intersection points. Anyway, here are our goals for today. The first thing we want to do is determine the number of points of intersection of a linear quadratic system and what the point of intersections are, what POE stands for. Determine the value for an unknown if you know the number of points of intersections. Alright, to solve a linear quadratic system, this requires determining the points of intersection. This can be done in a couple of different ways. We can do it graphically, graph the linear and quadratic relationship and see if and where they intersect. And we can also do it algebraically. We can set the two expressions equal to each other, rearrange to set equal to 0, solve the resulting quadratic, and determine if both solutions are admissible for real-life application questions. Now you may be wondering, why in the world would we actually care to solve this type of question? Let me give you a quick example. Let's suppose for a minute that you and your friends had enough guts to jump out of an airplane, and with the parachute, of course. And jumping out of that airplane, you fall through the air with some shape that looks like this. Doesn't look like a parabola? It absolutely is a parabola, right? You're a projectile in this moment. So you're flying through the air as a projectile, and then at some point you decide to pull your parachute. You pull your parachute, and all of a sudden you slow down. It doesn't mean that you're going to do this, all right? What it does mean is that you're going to do this. You're going to move at a constant velocity for the rest of the time. So if we were to graph a graph of your height versus time, we're going to see that it acts as a parabola when you're falling through the air. When you pull your parachute, you act in a linear fashion. And so if we find the point of intersection of those two, we can find what or when the parachute was pulled and how high off the ground it was. Now, notice something interesting here that you'll want to note when you get to some of the application questions in the homework. If you continue this straight line back, it's really hard for me to draw a straight line right on this angle like this, but if you do that, you'll notice that at some point, if I also continue the parabola backwards, there's another point of intersection. And so you're going to have the foresight and the application thinking to be able to know it's only the one that has a positive time that actually is real. The other one doesn't apply. Alright, so back to the note. Example 1 says determine the number of point of intersections algebraically. And part A is determine the number of point of intersections of f of x and g of x. So we do this simply by the following. We say I'm going to let f of x equal g of x. That means that 4x squared plus x minus 3 is equal to 5x minus 4. That's our first step. Set the two expressions equal to each other. Then we rearrange to set equal to 0. So we need to rearrange this, and I'm going to do that by subtracting 5x from both sides and adding 4 to both sides. And what that gives me is it gives me 4x squared minus 4x plus 1 is equal to 0. And if we're actually trying to solve for the number of points, for the points of intersection specifically, we would solve the resulting quadratic. We're going to do that in a minute. But this is only asking us for the number of points. It's not asking us to determine what they are. It says determine the number of points of intersection. Well, here's an important thing we need to keep in mind. The discriminant, which we've learned about earlier this unit, tells us the number of points of intersection. If there are 0 points of intersection, the discriminant is going to be less than 0. 1 point of intersection is going to be equal to 0. And if there are 2 points of intersection, it's going to be greater than 0. Well, how many points of intersection does this have? Well, let's use the discriminant. b squared minus 4ac is equal to, the b value is negative 4 squared, minus 4, the a value is 4, and the c value is 1. Negative 4 squared is 16. 4 times 1 is 16 as well. And so what you get is 0. That means it has 1 point of intersection. It has 1 POI. Now let's look at part B and actually find the point of intersection. What are the points of intersection? Show algebraically and graphically. again, let's go back up to the equation that we had right here, and let's use that in the third and fourth step listed above to do this. We want to solve the resulting quadratic. So how are we going to solve 4x squared minus, not plus, minus 4x plus 1 is equal to 0? Well, I can do that by factoring if I can. I can also do that by using the quadratic formula if I can't factor. Those are two methods that are very effective. So I'm going to see about factoring that. But I'm also going to recognize, wait a second, that looks pretty nice, and that looks pretty nice. Is this a perfect square? Well, let's check the middle term. Is the middle term 2 times the square root of that first term, 2x, times the square root of that last term, 1? Well, that's 4x, and it's negative 4x. So absolutely, we've checked the middle term, and it absolutely is a perfect square. It's just a quick way to show that without having to show it in its entirety. So now we can say that this becomes 2x minus 1, because the middle term is negative, all squared is equal to 0. I hope it becomes fairly obvious to you now what the answer is going to be. Taking the square root of both sides just gives me that 2x minus 1 is equal to 0, because the square root of 0 is still 0. And then I get 2x is equal to 1, divide both sides by 2, and x is equal to 1/2. Now what I do is I go ahead and I substitute x is equal to 1/2 into either one of the equations. And I'm specifically going to choose g of x because that's the simpler equation. That means g of x is equal to 5x minus 4, so 5 times 1/2 minus 4, which gives me 2.5 minus 4, or negative 1.5, which is negative 3 over 2. So that means that the point of intersection, algebraically speaking, is an x value of 1/2 and a y value of negative 3 over 2. Now, if I'd substituted this into f of x, the x value of 1/2, I would have gotten the same value because we're actually talking about the point of intersection. So I technically should have written this not as g of x, but I should have written the substitution as g of 1/2, because that's what the point of intersection is going to be. So if I now do this algebraically, I can take these two functions and graph those on the grid provided. So I take my function fx equals 4x squared plus x minus 3, and if I graph that, what I find is that I can graph it by finding the x-intercepts, and I'm going to just draw a scale here. Every 2 units will be 1. And so I'm not going to go over how to graph this right now. If you're having trouble with graphing that, that's a whole different thing. You should have figured that out by now in this unit. But your zeros end up being at negative 1 and 0.75. And your vertex ends up being at negative 0.125 or negative 1/8. And a y value of negative 2.8125. Yep. So I'm going to go down by 1 for every unit here, simply to get the other function, the g of x function, in. And negative 4, negative 5, negative 6. All right, so negative 1/8 and negative 2.8125 is right about there. And if I can get this thing working properly, you can see that there. It's going to be a parabola that looks something like this. And that's the function f of x. Now the other function that I need to graph is g of x. And g of x is 5x minus 4. So that means I'm going to start with an intercept at negative 4, a y-intercept, and I'm going to go up 5, rise over running of 1, and it's going to look something like this. And you can see, if I draw a line between these 2 points, then it's going to look, see how accurately I can do this. It's going to be tricky. See what I can do. It's going to look something like this, where it intersects the parabola at only 1 point. And it looks to me that it intersects the parabola. It's rough on this graph, but it's approximately 1/2. Actually, it's very accurate. It's 1/2 and negative 3 over 2, just like we found algebraically. Let's look at that last example now. If we're given the number of points of intersection, how do we solve for an unknown value? Well, in this case, the unknown value is represented by k. Oftentimes that will be the case. Given f of x and given g of x, determine the values of k if the two lines must intersect at two locations. So the first clue we have here is that if it intersects at two locations, the discriminant, b squared minus 4ac, must be greater than 0. Previously we looked at only one point of intersection, but if it's greater than 0, that means 2 points of intersection. So we're going to have to use this, and there's an important thing here at the side that we're going to use as we deal with that inequality sign, because we haven't done a lot of math with that in the past. This is the thing. It says when dealing with inequalities, you can add, subtract, multiply, divide like an equal sign. So you treat that greater than sign or less than sign, depending on what side of it you're on, as a normal equal sign. There's one exception. If you multiply or divide by a negative, which we're actually going to do, it's going to flip the direction of the inequality. But otherwise, that inequality is not going to change. All right? So let's see. B squared minus 4ac. Well, how do I get it to that point first? I first need to let f of x be equal to g of x. In order for us to do that, we substitute those functions in, and I rearrange to set it equal to 0, just like I did previously. So I'm going to subtract 9x from each side. I'm going to subtract k from each side, and what I'm left with is 3x squared minus 13x plus 9 minus k is equal to 0. So now the a term is 3, the b term is negative 13, and the c term is this 9 minus k. That k represents some number, so it is part of that c term. So we go to the b squared minus 4ac is greater than 0 for 2 points of intersection. And we can substitute that b value in. It's negative 13 squared minus 4 times a, which is 3, times c, which is 9 minus k. Has to be greater than 0. So we need to expand this out and isolate k. Negative 13 squared is 169 minus 12 times 9 minus k. And they just continue to expand this out using the distributive property. We get 169 minus 12 times 9 is 108. And then negative 12 times negative k is plus 12k. It's greater than 0. So what I'm going to do here is I'm going to bring the negative or the k over by subtracting it, just so you can see how this inequality would flip if we had to divide by a negative. So I'm subtracting 12k from both sides. 169 minus 108 is 61, and we have negative 12k over here. Dividing both sides by negative 12 gives me negative 61 over 12. But here we have that flipping of that inequality. Notice that that inequality flips. It's worth highlighting again. It flips when we divide by a negative. And so that means that k can be any value such that it's greater than negative 61 over 12. So let's say that again. K can be any value such that it is greater than negative 61 over 12. And you could substitute that back into the discriminant and check to make sure that would actually work. There you go.